Welcome to my presentation. My name is Arthur and I am a PhD student at TIB Leibniz Information Center for Science and Technology in Hanover, Germany. In this presentation, I will present you our recent work that deals with the requirements analysis for an open research knowledge graph. As all of you know, there is a huge amount of scientific articles out there. It gets harder and harder for us researchers to find related work and to stay up to date with the current research. One main reason for that is that scholarly knowledge is conveyed in plain PDF files and therefore not machine interpretable. We aim to reinvent scholarly communication by organizing scholarly knowledge in an open research knowledge graph. An open research knowledge graph shall interlink papers with subject-specific concepts like definitions, theorems, proofs, or methods in mathematics with each other and also between artifacts such as datasets or source code. Such a knowledge graph could reduce some of the current issues in scholarly communication, such that relevant research could be easier to find, research field overviews automatically compiled, and own insights could be placed rapidly in the current ecosystem. However, there are a lot of conflicting requirements, since we desire a comprehensive knowledge graph with domain-specific concepts, high granularity, high coverage, and of course high quality. The question is, how can we populate such a knowledge graph with such challenging requirements? Can we make some trade-offs and relax some of the requirements for specific use cases? To tackle that problem, we pursue requirements analysis following design science research. First, we analyze the desired functionalities. So what do you want to do with data? Then, when we know what the system should be able to do, we analyze which kind of data we need to support these functionalities. Do the ontologies have to be more domain-specific or more generic, and which granularity is necessary to represent scholarly knowledge? Next, we analyze the requirements on instance data. Which quality and coverage are sufficient for the respective use cases? Do we really need always high coverage and high quality? And last but not least, we elaborate suitable approaches to populate the knowledge graph. To analyze the questions, we first conducted an extensive related work, in particular about existing research knowledge graphs, ontologies representing scholarly knowledge, and manual and automatic approaches for knowledge graph construction. Then we elicited requirements by interviewing some of the ORKG group members and conducting a literature review about systematic literature reviews to get a better understanding of the workflow of researchers. Finally, we refined these requirements and elaborated possible approaches on how to populate the open research knowledge graph. Now I would like to present you our insights. Here you can find a small excerpt of our related work results. There are various existing research knowledge graphs, which mostly focus on metadata, citations, and artifacts. Diverse ontologies conceptualize scholarly knowledge from different points of view, and there are several manual and automatic approaches that have been employed for knowledge graph construction successfully. In particular, we found out that at the moment, automatic approaches on scholarly text achieve only a moderate accuracy. In this use case diagram, you can see the most frequent use cases for researchers. Please note that this only represents our perspective and that you may have a different point of view. Since we also want to understand your point of view, we have prepared a small survey, which I will share with you at the end of the presentation. The Open Research Knowledge Graph system should support researchers in the following use cases. First, the system should support researchers by obtaining up-to-date research field overviews. Usually, researchers conduct a survey article for that. However, once survey articles are published, they are not updated anymore. Further, survey articles represent only the perspective of few authors. Thus, the ORKG should maintain up-to-date research field overviews by the research community in a semantic manner. An open research knowledge graph should also support the find related work use case by employing semantic search engines which rely on knowledge graphs. For a natural language search query, the system should return the relevant articles without overwhelming the researcher with irrelevant articles. Then the researcher has to assess the relevance of the returned articles. Is this paper relevant for my research question? For that, the system should highlight the most important text passages in the paper. For instance, text passages that describe the research problem or the yielded results. The system should also support the researchers by extracting relevant information for the particular research questions at hand. Further, the system shall recommend further relevant research papers and also help to obtain a deep understanding of research paper by providing links to explanation videos for methods mentioned in the paper, or interlink mathematical equations in the paper with the corresponding implementation in the source code. Finally, the system should also provide all the necessary information to help to reproduce research results, such as datasets and source code. For that, the system relies on external systems such as data or code repositories, or explanations for certain methods on scholarly portals. Next, we discuss the requirements on ontology design and instance data for the identified use cases along the following dimensions. The first dimension is domain specialization of the ontology. Ontologies can be generic and consist of few domain-independent terms like process, method, or material, or be very domain-specific and describing, for instance, neural networks. The second dimension is granularity of the ontology. Ontologies can be very fine-grained, consisting of a lot of classes, attributes, and relations, or be very simple. The third dimension is coverage of the instance data. The instance data can have a high or a low coverage, thus contain all or only few possible instances for a given ontology. For instance, given an ontology with the class task, the instance data would have high coverage if all tasks mentioned in all papers are present in the instance data. The last dimension is quality of the instance data. For instance, is the p-value of a statistical significance test correctly provided in the knowledge graph? Are the research problems of the paper correctly assigned? In this table, we can see which requirements are sufficient for the respective use cases and therefore represent the trade-offs from our point of view. For instance, for the find-related work use case, a high coverage of instance data is very important since you do not want to miss any relevant articles during a related work search. However, the quality is less important since search engines employ latent feature representations and have therefore certain fuzziness. On the other hand, when I extract certain information from a research paper, for instance the p-value, then the p-value must not be wrong. However, missing information in the knowledge graph may be acceptable for that use case. We also identified that some of the use cases have quite similar requirements and have a high overlap in the ontology concepts and the instance data. For instance, the use cases extract relevant information and get research field overview may benefit from one another. If you have a research field overview that summarizes evaluation results for particular studies, then such an overview would also help you to extract relevant information for your particular research question. The use cases find related work and get recommended articles may also benefit from one another. If you have a fine-grained knowledge graph with high coverage consisting of scientific concepts like tasks, processes, and methods, then both use cases would benefit from such concepts in the knowledge graph. We also categorize the use cases. The first category depicted on the left side has high requirements on the quality of the instance data and high domain specialization of the ontology, but only low requirements on the coverage of the instance data. For that group, manual and semi-automatic approaches are more suitable for knowledge graph population to get high quality data. The second group depicted on the right side has high requirements on the coverage of the instance data and rather low requirements on quality of the instance data and domain specialization of the ontology. This group is predestined to full automatic approaches to get instance data with high coverage. Now let us conclude our results. The Open Research Knowledge Graph should represent the content of papers in a semantic way to enhance several literature-related tasks. However, the population of a comprehensive knowledge graph is very challenging, so that we have to make some trade-offs for specific use cases. We found out that use cases have different requirements on ontology design and instance data, and thus require different approaches for knowledge graph constructions. The first group of use cases has high quality requirements, and thus manual approaches are more suitable for them. The second group has high coverage requirements, and thus automatic approaches are more suitable for them. In future work, we plan to refine and implement the suggested approaches in an incremental process following design science research. We would also like to invite you to try out the current release of our Open Research Knowledge Graph and also get involved in the development. Further, we would like to invite you to participate in a small survey on Open Research Knowledge Graph requirements. We are very curious and excited to see your point of view on the requirements. In the end, we want to build a system that shall help us to simplify our research. So please participate in the survey to help us to build the right system for you. Thank you very much for your attention. Now I'm looking forward to discuss your questions.